Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos Ugobela Wemet. And without any further ado, let's look at these questions that we have here. Okay, so we have question 6. It says, in an experiment, a learner added 1.5 gram of sodium carbonate, Na2CO3, to hydrochloric acid, HCl, a volume of 306 centimeter cube. So note that we are given in cubic centimeters, and then we know that we should convert that to cubic decimeters by doing what? Dividing by 1000, right? And they say volume of 306 centimeter cube of carbon dioxide gas was formed and collected under standard pressure at room temperature. So once they mention standard pressure and standard temperature, we know that is STP, right? And the formula that comes to mind when we are using STP is obviously N is equals to V over Vm. Remember, we said this formula only applies to gases that are produced under STP, standard temperature and pressure. Then we are also given the molar gas volume at that room temperature is 24.45 dm cube. Now remember, note that we do have the Vm that is a constant from your data table, which is 22.4. But then I stated that if you are given the molar gas volume on that particular question, then you should refrain from using the 22.4 and instead use the one that is given. So this is the situation whereby if you are given the Vm is 24.45, that means we are going to use 24.45 instead of the 22.4 that we know. Right. Then the unbalanced equation for the reaction is as follows here. Then 6.1.1 says define the term 1 mole of a substance. So how do we define that? Quickly. So according to your CAPS document, you should define it exactly as it appears here. You say 1 mole is the amount of substance having the same number of particles as there are atoms in 12 gram of carbon-12. Right. Nice one. Then 6.1.2 says balance the equation for the reaction. So in order to balance, we can start by just writing our unbalanced equation, and that's plus HCl to give us, so I'm not writing the states, and then plus CO2. So what you can do here in order to balance this is list all the elements that are present. So we have our sodium, carbon, oxygen, and then hydrogen and chlorine. So that's the left-hand side. And also on the right-hand side, list accordingly in that order. So now in order to balance, you will check on the left-hand side, I have how many sodium atoms? I have 2. And then here I only have 1. So what's the number that I could multiply to 1 so that I have 2? So it's obviously 2. So just right in front of the NaCl, you will have 2 there. So let me use another color so that you can see where I balanced. So remember, we said we need to multiply it by 2. Then we want to take that 2 here and just put it right before the sodium there. But then how many number of carbon atoms do we have? On the left-hand side, it's only 1. But then on the right-hand side, also again, it's 1. And then when it comes to oxygens, we have 3. And then on the right-hand side, that's 1 here plus the 2 here. It's also 3. So it's balanced, 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 balanced. And then what about the hydrogens? Here we have 1. But then this side here, we have 2 atoms of hydrogen. So that means we have to balance on the left-hand side. So what number can we multiply to 1 so that we get 2? It's obviously 2. Then we have to check where we have 2 hydrogen atoms. So, where we have an hydrogen atom, so that we put the 2 there. So that's it. Now we have 2 hydrogen atoms. And then let's come to chlorine. Now, because of this 2, the number of chlorine atoms will now be 2 multiplied by 1, which is 2. right? And then also again here, because of this 2, the number of chlorine atoms will also be 2. So this one as well is balanced. And then we also have these ones balanced. So that means that's how we were supposed to balance this. So we were just supposed to put a 2 in front of the HCl and a 2 in front of the NaCl. So easy peasy. If you want a shorter way to balance this, that's how you go about it. Just list all the elements left and right, and then you do that. So you can come back as many times as possible and just try to understand this. So all for 2 marks, that means they only mark the 2 there and the 2 here. Right. Now let's move to 6.1.3. It says calculate the mass of sodium carbonate that reacted, and that is 7 marks. Now I know a lot of you, as soon as you see 7 marks, then you are already demotivated, but then that's not how I want you to approach this. Remember, I said with 7-mark questions, all you have to consider is that you need to follow the 3 steps of the stoichiometric calculations, which I was emphasizing on the first video that I posted on stoichiometry. So again, we can go through that. So we said number 1 is always to ensure that you calculate the number of moles. Any stoichiometric question will start by you having to calculate the number of moles. So calculate the number of moles, and then it's always the number of moles of the given compound or molecule. Now in an experiment, a learner added 1.5 gram of sodium carbonate to a hydrochloric acid HCl. Then they say a volume of 306 centimeter cube of carbon dioxide gas was formed and collected under standard temperature. Then the VM is 24.45. Now understand this, because we are looking for the mass of sodium carbonate that reacted, we cannot obviously use the 1.5 gram, because we understand the 1.5 gram, that's the maximum mass that was given. Now from this question here, we are getting that the sodium carbonate obviously is the excess reactant. That means not all of this 1.5 gram actually reacted, which is why they're saying we must calculate the mass of the sodium carbonate that reacted. If it was a matter of the 1.5 gram has all reacted, then such question wouldn't exist, right? So from this, we are getting that, okay, this must be the excess and this must be the limiting reagent, right? Now, in any question, we know that we must tackle it from the limiting reagent, right? Now, looking at this, we can see that we are given here, we are not given any information on the limiting reagent, right? But then we are given information on the carbon dioxide, which it is also acceptable to use that. It is a product that has been formed, right? And then it has been formed at STP. So in calculating our number of moles, we can use this information that we are given, which is the volume of the carbon dioxide gas and also the VM, right? The molar gas volume. So to start by calculating our number of moles, given the information that we have, it leads us to the formula N is equals to V over Vm, which we stated this is a formula that you only use for gases at STP. Now the volume, we have 306, but then we have already concluded that we cannot substitute the 306 because it's given in centimeter cube. We need to first divide it by 1000. So we go 306 divided by 1000. They should give us 0.306 cubic decimeters. Right, so we want to put it here, 0.306. Now, what is our VM? We are given 24.45. So we just go 24.45. Now, the number of moles that we have, 0.0125. I always advise that if you have not arrived to the final answer, always make sure to at least round off to 4 decimal places. In that way, you are not so far away from the true value. And then number 2 is to use the ratio coefficients. So number 2 is to use the ratio coefficients. Now remember, we have to note that what we are actually looking for is the mass of the sodium carbonate, but then the number of moles that we just found are that of the carbon dioxide. So if we can just compare the ratio of carbon dioxide to the ratio of sodium carbonate, Looking at our coefficients here, we can see that's a ratio of 1:1. But then a ratio of 1:1, we've already concluded that it means that the number of moles is equal. So the number of moles of the sodium carbonate also must be 0.0125 mole, right? Remember, this was of carbon dioxide, right? Because the ratio is 1:1, that means also the number of moles of the sodium carbonate needs to be 0.0125 mole. But then what are we looking for? We are looking for the mass that reacted. Okay, so step number 3 now is to calculate for the required value. So this is where now we get to calculate what we have been initially asked for. Now that we have the number of moles to calculate the mass, we can simply say mass is the number of moles over the molar mass. So the number of moles is 0.0125, but because we are looking for the mass of sodium carbonate, we have to use the molar mass of the sodium carbonate. So this will have, we will have to consult from our periodic table. The Na is 23. But then we have 2 of those, and then the carbon is 12, and then we have 3 multiplied by 16, right? Okay, so having to punch all that into your calculator, you have 106 grams per mole, right? And then this is what you're going to multiply with here, 106. Now, the mass that you are going to find is 1.33 gram. Right. And that's how you were supposed to calculate the mass. So for 7 marks. So note the steps that we took there. 3 stoichiometric steps. So number 1, you calculate the number of moles using the information that you are given. We are completely given the information of the carbon dioxide. So that enabled us to calculate the number of moles. Now from calculating the number of moles, we now have to take the ratio of this one versus the ratio of the one that we're looking for. Now after we find the number of moles of the one that we're looking for, we can then use that number of moles to calculate the mass. And that's it. Straightforward as that. So just make sure that you practice as many questions that involve you having to use those 3 stoichiometric steps so that you better understand it and you are confident about using it. Okay, so now we have a 6.1.4. So for that one, let me just erase this part here. It says 6.1.4, calculate the percentage of sodium carbonate in excess. Remember, we did mention that the 1.5 gram is the one that is in excess, or the sodium carbonate is the one in excess. And then we just calculated in the previous question that the one that actually reacted is 1.33 gram. If we want the mass in excess, now we do understand that we simply have to take the total mass over the mass that reacted, right? Now the total initial given mass was 1.5, and then the one that reacted, we calculated it's 1.33. And then we find that the difference in between is, so we can simply say 1.5 minus 1.33, we get 0.17 grams. Right. So that means we can simply just calculate the percentage in excess. It's only 2 marks by simply saying a percentage excess of the sodium carbonate. It's simply the one that is in excess or the unreacted, which is 0.17 gram, over the total, which is 1.5 gram. Then multiply that by 100. And then when you punch that into a calculator, you get 11.33%. So that becomes the percentage of the sodium carbonate in excess. So note how we did that one. And then fine. Okay, so now let's proceed to 6.2. Zinc reacts with sulfuric acid according to the reaction below. So we have that reaction, and then as we are not told here that it's unbalanced, so we assume that it's balanced, right? So if you are not told that it's unbalanced, then always assume that the reaction is balanced. The mass of zinc is recorded during the experiment and is shown on the graph below. The reaction stops after 2 minutes. So note that. Remember, in order for us to know that the reaction has come to completion, we will see the line being parallel to the x-axis, as we saw with the previous question. So always, when the line starts to be parallel to the x-axis, then it indicates that the reaction has come to a stop. So the reaction comes to a stop at 2 minutes, and then it's left there up until it reaches 3 minutes, but then actually the reaction came to a stop at only 2 minutes, right? So it's very important to note that. Now 6.2.1 says, name the substance that is the limiting reagent. Now looking at this, we can see that the reaction comes to completion, but then the mass of zinc is still 2 grams at that moment, meaning zinc was in excess. 5 to 2, that means only 3 grams of zinc reacted. Now we know that in a chemical equation, when we have 2 reactants, if one is in excess, then obviously the other one has to be the limiting reagent. It's always like that. You never have 2 excess reagent or 2 limiting reagent. If one is in excess, the other one is limiting. So in conclusion, we can say, if we have already concluded that zinc is in excess, then it goes without saying that obviously sulfuric acid is the one that is the limiting reagent. But then note it says name. So you are not supposed to say H2SO4. That's the chemical formula. To name it, you just say sulfuric acid. So the name is given up here, sulfuric acid. Now 6.2.2 says calculate the initial concentration of the sulfuric acid if 50 centimeter cube of the acid was used. Now again, 5 marks. We want to use our stoichiometric steps, right? Number 1 is to do what? Calculate the number of moles. Calculate the number of moles. Now, what can we use to calculate the number of moles? Now, if we check here, we don't have enough information to just straightforwardly calculate the number of moles of H2SO4, which is why we are involving the 3 stoichiometric steps. We are only given the information for zinc, but then what we are looking for is the sulfuric acid, the concentration of the sulfuric acid. So what we can say is that, okay, from this we can see that the mass that reacted of zinc is only 3 grams. So let's start by calculating the number of moles of zinc by saying mass reacted over the molar mass. The mass reacted from 5 minus 2 is 3. Then the molar mass of zinc from your periodic table is 65. Now you punch this into your calculator. You will get 0.0462, right? Remember, round off to at least 4 decimal places. And then number 2, use ratio coefficients. Use ratio coefficients. You will remember that we are not looking for zinc, we are looking for sulfuric acid. So we'll say, what is the ratio of zinc to sulfuric acid? Looking at our coefficients here, we can see that simply 1:1. So this means that if we have the number of moles of zinc being 0.0462, also the number of moles of sulfuric acid needs to be the same, because a ratio of 1:1 means that they have the same number of moles. Okay, then number 3, we said is now to calculate for the required value. Calculate for the required value. In this case, our required value is concentration. So number 3, I always say calculate for the required value because it goes back to what the question is looking for. If it's looking for mass, then your required value is the mass. If it's looking for concentration, then your required value is the concentration. So I hope that makes sense. Then your volume, note that it's given in cubic centimeters, which we do understand we still need to first divide by 1,000. So that's 50 divided by 1,000 is going to give us 0.05 decimeter cube, right? And then to calculate the concentration, it's C is equals to N over V, which will just give us C, our number of moles, 0.0462, and then our volume 0.05. And then that means the concentration now will have to be 0.92 mole per dm cube. Right. So that is the concentration right there. If you divide this one, we get 0.92 mole per dm cube. And that's how you were supposed to use that. So in this question, we had two questions that needed us to use the three-step of stoichiometric calculations. That was in 6.1.3 for the 7 marks and 6.2.2 for the 5 marks. So make sure that you play the video as many times as possible and just try to understand the approach that I took into solving this. And then hopefully at the end of the day, you are able to understand and be confident about using those 3 steps. But with all that being said, guys, please press the thumbs up button if you have enjoyed the lesson and then you found it helpful. And if you've been watching the videos and haven't subscribed yet, what are you waiting for? Please smash that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.